we want to try to determine which is the best approach to use under what circumstances. All right. So the concept of Lagrange multipliers is still dealing with optimization, but really specifically, we're dealing with the gradients. All right. So, I'll just read the blurb because I could paraphrase it, but it's always a disaster when I do that. All right. The technique comes from imagining that the function f has an extremum at a coordinate lying on the level surface S defined by g equals 0. We can construct any arbitrary curve defined parametrically that lies on S and passes through that point with the vector valued function given R, and then substituting this parameterization into f to form a new function h of t. Working out the implication of h prime of t sub o equals 0 at the extremum, it can be seen that the gradient is always orthogonal to any and all tangent vectors R prime. Since the gradient of g is also orthogonal to S, we get the gradient of f and the gradient of g must be parallel. All right, so that's one hell of a blurb, but basically what it's telling us is that, something that we already knew, that the tangent plane has to be horizontal at a turning point, at an extreme value. All right, and so what we get is a relationship. Right? Because we have two extreme values, the minimum and the maximum. The minimum and maximum values have to exist where a tangent plane has a slope equal to 0. So slope I use loosely because we're talking about a gradient. All right, so that gradient, time for a Spanish lesson. Later. I'm trying that Duolingo app, so it's not really going that well. I mean, it's going well, except I'm in very early stages. Like I'm learning things that I kind of already knew, like gender and like water and things like that. So I'm waiting for it to get to things that I haven't already known just by being a human being. So Spanish, if anybody's wondering. Oh yeah, I already said that. It's not for Spanish. But yeah, next up on my list is Klingon. So I'm going to try to become fluent in Spanish, and then I'll get to Klingon after that. So we'll see. Anyway, so yeah, if you know that the gradient vector has to be parallel to the xy plane for a maximum and for a minimum, then really you're just looking at one being a scalar multiple of the other. All right, so all we're getting at in this idea here is that there is some scalar that we're going to call lambda that is the scalar for the gradient vector. Now, you look at this and you see, if you go back to old school calculus, old school as in like prior to this course, you might look at that and think function notation, but that's talking about the first order partial with respect to x, y, and z. So collectively, these three give you the components of the gradient vector. All right, so if you know that f has to, the gradient f has to be some scalar away from being the gradient of g, and g or f, it really doesn't matter, f or g has to be equal to 0, then we can solve for that lambda value and come up with some meaningful relationships. All right, and those meaningful relationships will help us flesh out the x, y, z values that identify the extremes within the function. All right, so I mean that's the incredibly abridged version of it, but if you always have it in mind, just like when you were in Calc 1, if you had a turning point, it always corresponded with a horizontal tangent. Well, now you have planes that are going to be quote unquote horizontal. Their gradients have to be equal to 0. All right. So captured in between these two parallel planes must be the entire, the relevant part of the function, with the highest point tangent to the top plane and the lowest point tangent to the bottom plane. All right, so they're sandwiched in between these two planes. If we just figure out where those planes are, then we'll have what we need. All right. So I went a little crazy with GeoGebra. There really isn't a whole heck of a lot that you need from these diagrams. It's just, I was having too much fun. Actually, the first two are mine. Actually, the first, second, and then the second to last are all mine. The other ones I kept from, online resource, I think, but it could have been a textbook too. Only because I haven't yet figured out how to make the graph on GeoGebra look like those. I've been able to make it equivalent, but it doesn't look as nice. So what we want are the extreme temperatures on a metal plate with temperature function given, all right? So it's kind of weird to think about, but this is going to start to kind of give us a sense of how moving into the fourth dimension is going to work, because we have a function in terms of x and y, that's the temperature function, and they're telling us that we have that metal plate in the shape. Now, you might not be as up to snuff on your pre-calc, but and the reality is you don't really need to know that that is in the shape of an ellipse, right? But it is, you know, and so you got to figure that if you're talking about a surface related to temperature, that it's probably going to be some kind of circular-ish type region. You're thinking like the burner on a stove, right? So that's really what that's talking about. So it's an elliptical burner, which is not something I can really conceptualize in real life. I have never seen an elliptical burner before, but you never know. So maybe there's something to that. But what this is telling us is that the temperature varies along the surface of that burner, right? Which I think makes perfect sense. Now you could even conceptualize that to an oven. Like, there are certain parts of the oven that are hotter than other parts, right? That's why the directions tell you when you're baking to put whatever it is that you're baking on the center rack, right? Because that's the consistent temperature, right? Like when you put your oven to 350 degrees, the center rack is where it's going to hit that 350 degrees. The temperature is going to be different if you put it elsewhere. All right, so there is a function that will be defined based off location within that region, and that function is related to temperature. So this is telling us that there will be hotter or cooler portions of this plate. All right, and you know, ideally that wouldn't be the case if you have a stove that has an electric burner on it. Yeah, you'd like to think that when you put the pan on it, that it's going to be equally affected by that temperature change, but that's not always the case. You know, like as a stove gets older, some parts are a little bit hotter than others, right? So what we want to do is find the locations on this burner, this metal plate, the electric burner, that are the extreme values. So the hottest point and the coldest point, or coolest point. All right. So we're going to use the method of Lagrange multipliers. So we need our constraint function. Now the constraint is defined based off of this information here. I just need the outer boundary. All right, need the outer boundary because that's what the constraints will be. Those are the border, or represent the borders of this plate. All right, so what I'm going to do is rewrite this as x squared plus 4y squared equals 24. All the less than or equal to is telling us is that we're existing within those boundaries, which I think makes plenty of sense. All right. So I'm going to redefine this function by setting it equal to 0. So x squared plus 4y squared minus 24, that's going to be equal to 0. All right. Now they gave us a t of x. The rule, the Lagrange multiplier rule, talks about f of x, or t of x comma y. The rule talks about f of x comma y, but we can make that work. So I'm going to need my partials with respect to x and y. So very easy to do. So we're looking at 2x, sorry, plus 2, and then just a clean 2y. All right, this other function, at least the left-hand side, I'm going to define that as g of x. Lowercase. All right, so a couple of things that we would need to do. So I'm going to make a note of what g of x is equal to is I got to find the first order partials of this function, but then I also have to set that, well, set g of x equal to 0 and solve. Well, fortunately, it's already set equal to 0. I just have to actually solve that relation. Now, the issue is that relation has two variables in it, so the best I can do is solve for one variable in terms of the other. That's where the Lagrange technique is going to come into play. So I need g sub x, which would be 2x, and g sub y, which would be equal to 8y. Now, these two partials, or sets of partials, should only differ from each other by some constant that we call lambda. All right? So, t sub x should be equal to lambda g sub x. And t sub y should be equal to lambda g sub y. All right? Now, those rules made it look pretty crazy, but if you look at what we're actually setting equal, it's not really that bad. All right, so 2x plus 2 is going to be equal to lambda times 2x. And then 2y is going to be equal to lambda times 8y. All right, there is no z, we're not taking, we don't have a function defined in terms of x, y, and z, so I don't have to worry about partials with respect to z. All right, so I have lots of relationships here that I could play around with. It's just a matter of fleshing out what the value of lambda is. Now, you can see in the case of the first order partial with respect to y, I have a common y on both sides. So kill them. Basically divide both sides by 8y, and you'll see that lambda is equal to 1/4. All right, so then what I would want to do is pop that lambda into my x function. Simplify and solve, you'd be looking at 2x plus 2 equals 1/2 x. Bring it over, we're looking at 3/2 x is equal to -2. All right, so just subtracting the 1/2 x from both sides, subtract the 2 from both sides, multiply both sides by 2/3, you get x equals -4/3. I have like a little kink in my elbow, and then I cracked it, and I feel like I almost broke my arm. It hurts. All right, so now I just got to figure out the value of y that corresponds with that. All right, fortunately, I have my secondary equation. Because again, we really itemize the primary equation, which is the really freaking hurt. It's like when I cracked it, I think I hit the funny bone too. It's like, oh. The primary equation is the scalar multiple of the gradients. All right. The secondary equation is the g of x equals 0. All right. So what I have here, x squared plus 4y squared minus 24 equals 0. What I have here is a means by which I could find the corresponding value of y. All right. So we're living within this relationship. The y value that goes along with this x value is defined by this actual relationship, because in order for us to have satisfied Lagrange multipliers, this has to be a relationship that's true. So I could pop a -4/3 in here for x. Let me do that in red, actually. right, and then I'm just going to solve for y. All right, so it's not terrible. We got 16 over 9 plus 4y squared minus 24 equals 0. So 4y squared is going to be equal to 24 minus 16 over 9. I think that's 200 over 9. I'll double check that in a sec, but I just very quickly did that in my head, which is dangerous. Divide by 4, 50 over 9. So y would be equal to, two possibilities, could be plus or minus, the square root of 50 over 9. So you could simplify it if you want. It doesn't matter to me. All right, so if you take the square root and you simplify, you could get plus or minus 5 radical 2 over 3. All right, so this would be the y value that goes along with the x value. Now, we're talking about locations on a graph, right? Those locations are relative to the x, y, and z axis, because this is a z equal situation, so we're in free space. So it is conceivable that we could get positive or negative x values and y values, so we have to account for that. But now what I want to do is kind of flesh out, well, could be it's an extreme value, it could be a max or a min. So if there is an extreme value, it must come from this set of numbers, the x value of negative 4/3 and then y value, corresponding values of y. So now I go back to my original function and pop them in and see what I get. All right, so x squared plus 2x plus y squared I already forgot it. 2x plus y squared? Yeah, so I didn't forget. I wrote it wrong. 2x plus y squared. Oh, okay, no, we're good. All right, so I'm going to pop in a negative 4/3 for x. So I want to find negative 4/3, comma, negative 5 root 2 over 3. And then I want to find negative 4/3, positive 5 root 2 over 3. All right, so the computations is just a matter of squaring some things, moving some things around. So we're talking 16 over 9 minus 8/3 plus 50 over 9. Right, and it looks like, yeah, we're gonna get the exact same thing for the other one because the y value is squared, so it doesn't matter if it is positive or negative. I'm just making sure I didn't, yeah, no, it looks like it. So, let's see. 66 over 9 minus 24 over 9, so 42 ninths. Minus 24 is 42, right? Denominator, boom, boom, boom. So it looks like we have two distinct locations where we're going to arrive at an extreme value, all right? So they asked us find the extreme temperatures on the metal plate, all right? So 42 over 9, seems kind of low. But we also don't have units here, so I don't know necessarily whether it's unreasonably low or otherwise. And also, again, I did a couple of things in my head where I probably shouldn't have. Well, 24 times 9 is 216, right? This is the part where you tell me if I'm right or wrong.
Yes.
Yeah. And then 216 minus 16, that's obvious, that's 200. 50 over 9, so I think that's good. 5 rad 2. Yeah, it looks, I mean, I'm not seeing anything glaring, but like, it's kind of alarming to see an extreme temperature of 4 2/3 degree. Well, that would be extreme on the low side then, I would think. Yeah, so. Yeah, exactly. It's practically the absence of heat. So, there you go. So this is the extreme temperature. All right, there was no indication that we needed to determine whether it was a max or min, but I would venture to say that common sense would kind of dictate that this is going to be a minimum. Based on a lot of the things that I just got through saying, like 4 2/3 of a degree, that seems incredibly low to be a maximum temperature. But also, if you look at all the diagrams, they're upward facing paraboloids of some way, shape, or form. Okay, so that's going to give us a minimum on that. So yeah, that is the technique of Lagrange multipliers. And really, its difficulty level is only related to the type of function that you're working with. So we had polynomial functions. If we had something more complicated, obviously it'd be a little bit trickier, but that, like I said before, a very simple concept. It's just a matter of implementing. All right, so for the next one, you can see the same general structure. This one you don't really have a graph to rely upon because, I mean, I don't even know what the meaning of this graph would be. This would be in 4 dimensions. All right, so profit a company makes by producing X, Y, and Z thousand units of products is given by that. If manufacturing constraints force that relationship, find out production parameters for maximum profit for the company. So we know that we have to have a maximum out of this. So what we're going to do, again, is redefine our constraint function to be a g of x. So we're going to say x squared plus 4y squared plus 2z squared equals 800, because we only care about the outer boundary. We're going to bring the 800 over. And then we get to work on our partials. So we're going to find partial with respect to x, y, and z. This guy over here is my g function, so g of x, y, z. So I'm going to find my first order partial with respect to x, y, and z for the g function, the constraint function. All right. So for my p of x, y, z, not difficult at all. 4, 8, and 6. For the other one, a little bit more work, but nothing dastardly. We have 2x, 8y, and 4z. And again, there's going to be some lambda, some value of lambda that allows the corresponding partials to be equivalent to one another. All right, so what I would say is that, and I could just kind of tuck it in over here, 4 is equal to lambda times 2x. 8 is equal to lambda times 8x. And 6 is equal to lambda, poor quality lambda, still poor quality lambda, lambda times 4z. All right. And so, 8y, sorry. So in the first case, we can't directly solve, actually in any of the cases, we can't really directly solve for lambda. So this is an instance where we have a little bit of an issue because it's like, well, where's lambda equals like the last problem? But what we can do is we can solve for lambda itself, you know, in terms of another variable, right? So we'll get a relationship between multiple variables, and so we can kind of live with that, right? So lambda would be equal to 2 over x. Lambda would be equal to 1 over y. And lambda would be equal to 6 over 4z, which is 3 over 2z. All right. Now, we can go in another direction here. We could solve for, so we solve for lambda. We could also take it a different way. We could say that x is equal to 2 over lambda. Y is equal to 1 over lambda. And z is equal to 3 over 2 lambda. So all these different variations are just really designed to give you a blueprint, or not even blueprint, we have a blueprint. Necessary ingredients to carry out the plan. Okay? So what I know is that x squared plus 4y squared plus 2z squared minus 800 is equal to 0. And now I have what x, y, and z are all equivalent to in terms of lambda. So I can take that entire function and replace each of the values of x, y, and z with a corresponding expression related to lambda. All right, so, that is not a marker. Let me make the arrow a little bit longer. So, x squared plus 4y squared plus 2z squared minus 800 is equal to 0. All right, so 2 over lambda, 1 over lambda, 3 over 2 lambda. Lambda, lambda, lambda. So we have 4 over lambda squared plus 4 over lambda squared plus, well, the next one's a little bit different. So we'd have 2 times 9, so 18 over 4 lambda squared. So the best I can do, so 18 over 4, 9 over 2 lambda squared. Minus 800 is equal to 0. All right, so basically I'm just killing the outside 2 with one of the 2's on the bottom. All right. Now, it's a fractional equation. I know lambda can't be equal to 0. It'll make it undefined, but really, if you think about it, we're looking for a scalar that would make one gradient into another. I don't want it to be 0 anyway. All right, so what I'm going to do is multiply it by lambda squared throughout to kill all those denominators. You know what? While I'm at it, multiply by 2 to get rid of the 2 as well. All right. You might want to combine like terms as you go, but you know, it's all going to come out in the wash anyway. So we're looking at 8 plus 8 plus, I'm sorry, 8 plus 8 plus 9 minus 800, nope, 1600. Lambda squared is equal to 0. All right, so we got what, 25 here? minus 1600 lambda squared is equal to 0. Perfect square values, that's nice. I'll take that. Subtract the 25, divide by 1600, you're going to get 25 over 1600. But then when you root both sides, you get lambda is equal to plus or minus 5 over 40, which is 1 over 8. All right, so plus or minus 1 over 8. So lambda could be two possibilities, but that's good. You know, I was going to say that's good news. It's news. It doesn't matter because we have a relationship between x, y, and z all with lambda. So now I can figure out what the x values, y values, and z values are going to be that correspond with this lambda. So again, x is equal to 2 over lambda. So I'll just jot that down. Y is equal to 1 over lambda. And z is equal to 3 over 2 lambda. All right. I'm going to do it one at a time. So at lambda is equal to 1/2. 1/8. We're going to get the x, y, z coordinates. 2 over 1/8 is 16. 1 over 1/8 is 8. And 3 over 1/4, because 2 eighths, so 3 over 1/4 is 12. All right. At lambda is equal to negative 1/8. We're going to get the same stuff, just negative. It's just I didn't want to do it all in one shot because if I did, sometimes you kind of get your wires crossed in terms of which x goes with which y. It's all the positives go together, all the negatives go together. All right. So we do have to answer the question that's being posed. It says, find the production parameters for maximum profit for the company. All right, so the parameters again are x, y, and z thousands of units. All right, so it makes it seem, I think rightly so, that the negatives wouldn't really make sense here. All right, so what I would want are, because it's in thousands of units, so 16,000 of x, 8,000 of y, and 12,000 of z. And that's really it. Now, there's always a concern when you think about Calc 1 and when you're finding maximum and minimum values. Remember you had to make sign charts where you had to do the second derivative test. It's kind of like an unnecessary step in a lot of cases because the question asked you to find a maximum and then you only got one critical value, so you knew it had to be the maximum. This is along the same lines. Technically, we should vet that 16, 8, 12 and make sure it's not giving us a minimum. Because you wouldn't want to produce 16,000 units of something, 8,000 of another, 12,000 of another, and find out that's going to give you the least profit, right? So that would kind of stink. But, you know, common sense tells it. I mean, it's the only relevant value. It's got to be the answer to the question, all right? But what you can do, and really it's actually a very simple process. Just pick another point that you know satisfies the constraint function that's near 16, 8, and 12, and pop it into your profit function. See if it gives you a number that's smaller than whatever the profit would be if you plug this in. All right, so it's really not bad. All right, so it's guess and check / unnecessary busy work to the point where I don't even like encourage people to do it. Now, if you come up with a model for your business, like you actually go into business and you're using something like this, first off, I'd be shocked. Second off, like, yeah, you would check your work to make sure you're not going to go ahead and produce 16,000 items and find out it's going to make you like worse for it. But that's a natural situation where you would check it. I'm not overly interested.
Is this something that people actually do?
It's built into the software that people use when they're actually doing this sort of thing. Like what people actually do compute what the optimal number of values items produced should be. It's just they don't sit there making a multivariable equation. That's built into the code that's in the software that they use to determine it. And so, like for example, I experience this pretty much all the time, but it's the vergence, I would say, of life and math class for me always, it strikes me as something that's interesting. So once every couple of years I go to Marshall's because it takes me about 2 years to go through cologne. Right? So I like the David Beckham cologne. I just, I can't, it might be something called Instinct or something like that. It's at home. But I'm down to there's like a tiny little puddle left. But, I'm 2 spritzes in the morning, and then that's it, And so it lasts me about 2 years. So 4 years ago, I went to Marshall's, and I bought my first thing of David Beckham cologne. And then 2 years later, so 2 years ago, I went there again, and I got another one. And so I went there again this past week, figuring, all right, I'm due. Let's see if they have my David Beckham cologne. They did not. So now I don't know what I'm going to do, because the whole idea behind going to Marshall's is you get something that's normally pretty expensive and you get it on the cheap. All right. So I went there thinking, okay, I'll get my whatever it normally costs, like $100 cologne for the $15 that I normally pay for it. So now I'll have to hunt around for it online. Actually, they don't have it. So probably it causes some sort of skin disorder or something. I probably shouldn't be using it anyway. The second thing I went in there for is these puppies right here, the Columbia fleece zip-up sweaters, right? So I went to Costco the other day figuring, all right, I'll just get it from Costco. I tried it on, and then when I took it off, my shirt was covered with the fuzz that was on the inside. I'm like, that's no bueno. I'm not going to be able to work with that. So I went to Marshall's figuring, all right, last one I got there also. So if you've ever been in Marshall's, you know that it's all overstock from different department stores. So high-end department stores, brand name stuff, but if it ain't there, it's not like they have a storeroom that they're going to go into. They don't have things on back order. It's just whatever didn't sell at Macy's is getting dumped over to Marshall's. So I'm in there hunting around looking for my size. I need a 2X. All right. It took me about half an hour, but I found what I was looking for. So the reason I bring this up is because there was about 40 extra smalls of this zip-up jacket. And so all I'm thinking about, aside from the fact that I'm teaching this in this class, is, man, somebody didn't do their calculus homework. Because if they did, they would know that they didn't need to produce as many extra smalls as they actually did. Right? The fact that there were only 2.
Buy that many extra smalls.
Right. Yeah. Like the buyer of the store, of Macy's. Yeah. They bought too many from the manufacturer. So they didn't do their homework, because there is a function out there that you could use to model how much of an item you need to actually have in production. Right? And so if you optimize it properly, then you can have that information. Now again, I don't think people are going to sit there with their graphing calculators and differentiating these functions. What they're going to do is use appropriate software to make that determination. But generally what manufacturers do, especially for clothing, is they follow a normal distribution. Right? And so they determine what the appropriate quantity would be to produce based off of that normal distribution. The problem is it's strictly dependent on the mean and standard deviation for a population. So if their information is outdated, they're going to get the wrong distribution, right? But together with the concept of a normal distribution and optimization, they could come up with the ideal value. Because in theory, I mean, I was lucky to get the 2 sweaters that I got. I got one in one color and one in another. But in theory, there shouldn't be anything for Marshall's to sell, right? Because if you do the math right, then there's all of the stores like Macy's, JCPenney's, I don't even know if that exists anymore. But all of those caliber stores, they should be able to have the exact quantity that they need and be able to sell it all and not have any overstock to sell to marshals, right? So this stuff is incredibly powerful, but again, yeah, you're not sitting there with a graph calculator figuring this out. You're using software to make the determination for it. But it's a skill, and I'll tell you right now, it's a skill that lots of people are lacking, because what happens is, and I'll get off my soapbox in a second, people apply for jobs in these industries, and they're not qualified for the jobs, but they interview well, so they get the jobs. And so what happens is they don't do a good job once they're there, and it takes a little while for people to discover that they're woefully underqualified for that job, and before you know it, they've ruined the industry. So yeah, you got to interview well, but also it helps if you know at least conceptually a lot of this stuff. All right.
Math with knows really well. You can make millions after that.
Absolutely. Yeah, but the thing is, you gotta know the math, but you got to know how to market yourself. That's the thing. And I find that there's often an inverse relationship between the two things, because in my experience, the people who, and this is completely anecdotal, so it's not a fact, it's not a rule, but in my experience over the years, the people who are the best at math are the least personable. And it's like, oh, you just offended me because I'm really good at math and I'm very personable. It's just over 20 years, if I did a percentage, just a statistical analysis, just looking at percentages, overwhelmingly, the ones who are the most gifted in the areas of mathematics are also the least personable. And so how do you market yourself if you're not attending to those other aspects of your life? Right, so you gotta make one go along with the other. Right, so all right, off the soapbox.